just some food for thought, or actually just get thinking exercise. I'm a little bit curious, and I haven't really looked into this, which means that there's probably an answer out there that I haven't seen, but I'm a little bit curious to know what would be um, the best PTO arrangement for employees. Because I was thinking about it, I know that there's some companies that offer unlimited PTO, right? And well, not in civil engineering. Civil engineering companies don't give anything, but some companies in decent careers offer unlimited PTO. But usually that comes with conditions, right? That it's unlimited PTO, but of course it needs to be approved by your supervisor. And I've kind of wondered, would offering unlimited PTO in the end be cheaper to the employer or not? Because if I give my employees, let's say 2 weeks of PTO, right, per year, and let's say that it accrues, so if you don't use it 1 year, you have maybe 4 weeks the next year. But usually for accruals, there's a limit. They say you can have up to 180 hours or something, or up to, I don't know, 120 hours, but no more than that, because employers don't want their employees taking 3 months off, right, with pay. Normally PTO, when it's limited, when it's like a limited amount, usually employees have more flexibility of using it. But if they are going to run out of their time, right, of the amount of time they can accrue, then they have to use it. Otherwise, they lose that money, which is money that they've earned, right? It's a benefit, but it's a benefit that was part of the agreement when they originally joined the company. So basically, giving your employees a fixed number of hours encourages them to use those hours, right? So I'm thinking, if you give your employees an unlimited, a non-fixed number of hours, would the employees end up using more or less of the time? I feel like there's some data out there that should probably give us the answer to that. Yeah, unlimited. That's something that some companies do, which it's a bit of a trick. I would say be careful, right? Be careful because they say unlimited, but of course you need to have approval from your manager, right? So I see. So some companies do that, they never approve it. Okay, so interesting. So I'm glad that you have some experience with that, because I've never had experience with that. I've only been a civil engineer, and like I said, civil engineering companies are the worst when it comes to benefits. I mean, you can ask my interns; they'll tell you civil engineering companies are the worst when it comes to benefits. But I was just thinking about that. I don't particularly care. I just thought it would be, I don't know, something fun for an exercise or maybe a test problem. But I gotta see if I can find data on that. Let's move on. Let's move forward. I know that we spent the first half of the class going through an example, but I think it was a good example because we were able to review everything. So now I don't feel any moral obligation to review the material for later because we have this example that gives us everything we need. What I would like to do now is talk a little bit about how we can organize our data. And if you look at your notes for this week, the first couple of sections of our notes are about different joint probability distributions. So different ways we can organize our data into joint probability distributions. We're not really going to cover them in class, and you won't really see them outside of the, let's see, the 3 problems that are assigned for the homework. I'd say these are more assigned just so that you can have a well-rounded education in the area of joint probability distributions. But as far as our work goes, especially for you, future civil engineers, I do feel that we've covered what we need regarding joint probability distributions. I think with what you have, you should have the tools to be able to apply these to your transportation or your meteorology, hydrology problems. But when you have your time, read through those 3 sections. They're very short. One is multinomial probability distribution, one is the bivariate normal, and one is about linear functions. And you can go through some examples if you want. You can get a bit of an idea of those sections. Just to give you a super quick summary, multinomial is essentially the binomial probability distribution, but generalized for multiple outcomes. So binomial is success or failure. Multinomial is generalizing that. Instead of success or failure, it can be success, maybe something else, something else. So you can have multiple outcomes, not just two. That's the difference. The bivariate normal is a two-dimensional normal probability distribution. So it's a joint probability distribution that's normal. If you look at it, it actually looks like an actual bell, like a three-dimensional bell. So a normal distribution is a two-dimensional bell curve. A bivariate normal is a three-dimensional bell curve. It looks like a 3D bell. If you draw a cross section right through any of the axes, you'll get a normal distribution. And then linear functions just consists of linearizing our work. In other words, taking our random variables and making linear functions of those random variables. And then we can calculate their means and their variances and treat them as one function instead of multiple random variables. It's a way to take your joint distributions and then simplify them into one variable. I don't think we're not really gonna cover them beyond the 3 problems in the homework. I would recommend that if you are interested in the subject that you read through them. But the focus on the rest of today's class is actually going to be on the numerical measures that we use to organize our data, which is something that I've actually been looking forward to talking about for a while, because talking about these numerical measures is actually going to help us. It is going to help us with some of our discussions. Sometimes I want to talk about medians, I want to talk about modes, but because we haven't really discussed them properly in class, I've had to wait. So today, I would like to talk about numerical measures of data. So the first thing, right, is that once you've collected your data, you've gone to the field, you've obtained your measurements, we need to know how to organize it, right? Now, part of organizing data is about recognizing patterns, right? Generating probability distributions. You want to identify which type of distribution your data falls into. And that is going to require a keen eye, a keen statistical eye. So you need to understand the experiment that you're conducting in order to know its probability distribution. You also need to have a good eye in looking at your data to see if you can recognize what type of distribution it follows. One way that we can analyze our data mathematically is by calculating our measures. You may recall that we had 3 main measures: mean, variance, and standard deviation. For joint probability distributions, we had 2 more measures: covariance and correlation. So if we can find our measures, that allows us to describe our data. Now, we've seen some very common distributions, right, for single variables, and we've used them. That's good. But now I'd like to look at a different way, a different method that we can use to analyze our data, and that is through numerical measures. Right? We've already talked about mean, variance, standard deviation as some of our measures. These numerical measures are actually going to be a little bit different. So what makes them numerical measures is that they do not consider the probability of outcomes in a random variable. Instead, these numerical measures take our observations at their face value. Now, what I mean when I say at face value is that the numerical measures basically consider every single observation, every measurement in your data set. Whereas a probability distribution can look at each individual outcome and then assign a probability to it. Our numerical measures don't do that. They, instead of looking at each individual outcome, it looks at each individual measurement, which means that multiple measurements could have the same outcome, but it doesn't consider probability. Instead, it considers some of the measurements themselves. The first of these numerical measures is actually one that you already know. You may think you don't know it yet, but you already know it. You already know it, and that's the sample mean. In short, the sample mean is what most of you answered when I asked if you knew what the mean was. You said add everything, divide by the number, right? That is actually the sample mean. It's essentially an arithmetic average. So I say that x bar is the arithmetic average of my random variable x, which consists of adding each individual measurement in x from I equals 1. Let's say there's n measurements from I equals 1 to n, and then dividing it by the number of measurements. So in here, each individual measurement is x of I. You can call it measurement, you can call it observation as well. And n is the number of measurements or observations. So the sample mean is what you typically call the average, right? The average, arithmetic average or average. I look at an exam, I give an exam, and I say, I would like for you to, to determine how well you're doing within the, compared to the rest of the class. What I can do is I can take everybody's grades, add them up, divide by the number of students, and say the average grade for this class is this much. And that is a sample mean, right? The average, the arithmetic average. That is the first numerical measure I want to talk about. You'll notice that sample mean and mean are only the same when my probability distribution is uniform. If my probability distribution is uniform, I think Samuel said it a little bit earlier today that the probability is 1 over n. So if my probability distribution is uniform, then the sample mean and the mean are the same. But in other cases, the sample mean and the mean will not be the same. And that's why it's important to understand what the sample mean is and what it tells us and how it differentiates from the actual mean. I really like giving my students averages in their tests so that it keeps students humble. So that someone's like, oh, I did very well. And then you see the average, oh, actually, I didn't do that well compared to everyone else. Or I did very badly. You see the average, oh, I actually did better than I thought I did. I enjoy giving out averages to my students, normally in longer tests, like my fluids tests, which are like huge. Anyway, this is the sample mean. Now, you may be thinking, well, if there is a sample, then there's probably a sample variance. And that's right. There is a sample mean, right, that considers the samples at face value. There's also a sample variance that looks at the dispersion of those samples. Again, we're looking at the samples themselves, not at the distribution of probabilities. So by doing that, we can calculate what's called the sample variance. My sample variance, typically written with a lowercase s squared, so we went from Greek letters to Latin letters, is going to be equal to the sum of x, each individual value x minus the sample mean squared, and this is from I equals 1 to n, divided by n minus 1. Notice that the equation is actually very, very similar to the variance equation. Variance equation was the sum of each individual outcome minus the mean squared times the probability. And that probability, as we can see, we treat it here as 1 over n, so almost as if it were uniform. What's a little bit different here, maybe a little bit strange, is that we do have an n minus 1. Now what happens is that different calculations with different data sets have shown that the sample variance is always going to be smaller than the variance. So in order to reconcile the sample variance and the variance a little bit, we actually subtract 1 from our number of measurements, which makes this sample variance slightly larger. And by making it larger, we actually allow it to be a little bit closer to the variance. Personally, I don't really understand the math behind this. So I'm just gonna, explain what the textbook explained, which is what I just said. So we will leave it at that. But essentially n minus 1, the minus 1 is like an adjustment, like a correction that we do to the sample variance. The sample variance can also be derived into a different way. If we were to take this expression and expand it, so x minus x bar squared, if we were to expand this, then we can come up with another way of representing the sample variance. And that is the sum of all my variables x squared from I equals 1 to n minus the sum of all my variables x from I equals 1 to n squared divided by n, and all this divided by n minus 1. So if you take this mathematical expression and you were to expand it, you can land at this alternate form of the sample variance. We're not going to do the derivation in class, like I said, but you will get a chance to do it for your project. Finally, we're going to look at the sample standard deviation. And I'm going to need a brave student to try to guess what the sample standard deviation would look like. Yep, that's correct. Square root of the sample variance, not variance, the sample variance. That's correct. And that's true. Sample standard deviation. Good. So these are my 3 numerical measures. We call them numerical measures because they take the observations at face value. Okay, take the measurements, the observations at face value. Sample mean, sample variance, and sample standard deviation. You'll notice that unless your probability distribution is uniform, your sample mean and your mean will not actually coincide. So it's important to know both measures in order to help you understand your sample space, your data set. So that is, or those are my 3 most important numerical measures. There are other numerical measures that we're going to use in this class. Some of them are pretty straightforward. For example, the range. Sometimes understanding the mean is helpful, but not really helpful. For example, let's say that, and I'm going to try to use education as the example just because it's the one that's, I can just come up with examples in the fly, but let's say that I am trying to identify, which sections of a particular class require special help. Perhaps we're trying to put together a tutoring program, okay? And what I'd like to do is I'd like to put together, right, a list of students or at least, a list of students that could potentially participate in this tutoring program. Now, I could go through each individual section and look at the mean, right, the average grade of that section. I could even try to look at the variance to see how those grades are dispersed. But even looking at the mean and the variance doesn't really tell me what my extremes are. In other words, maybe the mean of a class is 70, okay? And I think the averages in my classes are usually around 70-ish. It could be a little bit higher, but let's say 70. Now the question is, from that number alone, from 70, I can't really tell if there are students in that class that can participate in the tutoring program, so that can be tutors, or if there are students that need the program, that will be, I don't know, tutees, I don't know what you call that, but the tutored students. However, the range essentially tells me specifically how spread out my data is. My range is going to be equal to the maximum value in a data set minus the smallest value in a data set. So my range can give me a better idea of how far away the extremes of a data set are from each other. It also gives me a good idea of what values my data set covers, which will allow us to generate frequency distributions, which we'll talk about later, or generate nice graphs, which we will talk about on Wednesday. So range gives me essentially the overall coverage, okay, of my data set. You already know domain and range, right? So that's where range comes from, yeah? So the range is another numerical measure. Then comes my favorite numerical measure, and that is the sample median. In this class, we'll just call it the median, okay? Now, what is the median? If we were to arrange all our values in ascending order, then the median is the middle value. And this is if my numbers are odd. If my numbers are even, if I have an even number of points, which means there is no middle value, then the median is going to be the average or halfway point of the two middle values. Okay, so that is my median. I love the median. In fact, for me, and most of the applications that I tend to use numerical measures, the median is more helpful. Now you'll realize that there isn't one that's more or less helpful than the other. It really depends on the application, on what it is you are trying to do. Now, in this class, we are going to look at different scenarios, different data sets where you will choose what numerical measures to emphasize depending on what it is you're trying to show or prove from your data sets. So median is the middle value, and you get it by organizing all of your measurements, all of your observations in ascending order. If there is no middle value, you take the two central values and then you average them out. In other words, you find the halfway point between them. Another numerical measure is the mode, also known as sample mode. The mode is the most recurring value in a sample. In other words, the value that is repeated the most. You'll find again that our mode really becomes helpful for some applications, less helpful for others, okay? If there is no value that shows up more than once, or if there are multiple values that show up the same number of times, then a sample will have multiple modes. So it is possible for a sample to have more than one mode. In this class, we may try to focus on the cases where there's only one mode, just for simplicity. So these are my 6 numerical measures. They seem significantly easier to use than the measures that we've learned earlier: mean, variance, standard deviation, covariance, correlation. However, they are very, very, very powerful in that they can help us identify, present, understand, analyze various data sets, which is very, very important. I bought a book not too long ago. It's called How to Lie with Statistics. Really wonderful book. And the second chapter of that book already dives into the difference between sample mean, sample median, and mode, and how you can select each of these values to essentially push forward your own agenda, right? To essentially prove what it is you are trying to prove. These values, right, are very important when it comes to understanding data sets. Now, I would like to see if maybe you can help me a little bit, and hopefully by helping me, you can understand how these values work. When I bought my first home, this was several years ago, actually, right after my master's. I pretty much bought a home in a good area, but in the cheapest neighborhood in that good area. So I moved to a pretty decent decent city, right, with a very, very high median income, extremely low crime rates. Mine was practically nothing when I moved there. It's actually a little bit higher now. Maybe it's because it's not because of me. But I moved to a pretty good area, but I moved to the cheapest neighborhood. And one of the things I noticed was the different measures that were used, right, to promote that neighborhood. You see, the houses in that neighborhood were all pretty much in the high 100s, low 200s range. But at that neighborhood, in recent years, a lot of actors have moved into the neighborhood, because we have a lot of studios now here in Georgia. Pretty much everything that's worth watching is being filmed and produced here in Georgia. So naturally, you're going to have people that work in the film industry moving into the suburbs of Atlanta. Now, of course, by someone with a higher income moving to a house, you typically expect if we have a good selling realtor, the selling realtor is going to want to get as much money as possible from that sale, which means that even though my neighborhood was in the range, let's say average 200,000 range, there were still some houses that were sold for a lot higher than that. So my question is, if I were a realtor and I'm promoting a neighborhood and I want to show people how upscale the neighborhood is, and I want to show people how upscale the neighborhood is by, let's say, by showing what the maximum price of a house is, but then also maybe showing some sort of numerical measure here, okay? And assuming that most of the houses are pretty much at let's say a decent middle class range, and only some houses are at a high range, which of these 6 measures do you think would be more useful for the realtor as they try to prepare or promote this neighborhood? The sample mean? Okay. So why do you think the sample mean would be more useful? I'm not saying you're wrong. I just want to know why you would think that's more useful.
I feel like the median and mode don't necessarily depend on the higher houses. They're just in the middle of the values. It doesn't matter how high the highest is. But the sample
Mhm.
mean, those extremely expensive houses are going to raise that value if you want to make it seem more expensive. Yeah.
Exactly, exactly. You want to make your neighborhood seem more expensive, and you know that the extremes are typically on the upper level. You want to use your sample mean. Correct. That's absolutely right. If you don't understand it, it's fine. We'll do a numerical example actually, so you can see it in action. But now let's move forward. Let's say that I am now advocating for lower property taxes, which is actually something that I would do. Who wants to pay more property taxes, right? So let's say that I'm advocating now for lower property taxes, and I am trying to assess, right, the house price in my neighborhood. My neighborhood has different houses. As you can see, they have more or less different prices. But I want to assess, I want to give a value, a number from one of these measures that gives me, okay, that gives me a nice representative price of a house in order to help, in order to help institute fair property taxes for all or at least the majority of the homeowners. In this case, what would I want to use? What measure would I want to use? I want my houses to seem cheaper. I want my neighborhood to seem cheaper now because I'm not trying to sell it to anyone. Now I'm actually trying to lower my property taxes. What would I use? If we look at this data set, we can say that the mean would fall, let's say, it could fall somewhere here, the mean. The median, good, because the median, right, it's the middle value, it's going to fall somewhere here. Or the mode if it helps us as well. Thank you, Christian. That's absolutely right. I would say for this case, mode may not be helpful if we're looking at prices to the dollar, because 2 houses in the same neighborhood won't exactly sell for the same price. There's a lot of negotiating going on, so there'll always be a couple $1,000s less or more, right? However, if instead of looking at individual prices, if I'm looking at a range of prices, let's say 190 to 210, and I lump in as much houses as I can in that range, then I can use the mode, and the mode can represent the most recurrent range in my data set. So that, I think both answers are correct. I would probably go with the median just because it does take less work on our end, right? You try to use mode, then you are going to end up having to justify how you split up your values, right? So yeah, median would be a good value, a good measure to use. People will use the mean and median all the time, depending on what they want to show. Whenever you see or hear someone say the average person earns this much, the average this, the average that, you have to be very, very careful because you don't know if they are talking about mean, if they are talking about median. Daryl Huff, statistician, calls this the well-chosen average, also from the Lying with Statistics book. The well-chosen average, essentially, right, is an average that's going to give you or give the reader the impression that you want to give the reader. For example, I'm a business owner. I make a lot of money, and maybe a small circle, a small inner circle makes a lot of money, and then everybody else gets paid dirt cheap. But I want to show the world how benevolent I am, especially in this day and age when somehow people are against successful people. So I want to show everyone how benevolent I am. If I want to show everyone how benevolent I am, what I could do is I could come up with a list that gives me, right, a document, a publication that gives me the average rate of pay or the average pay of employees in my company. But of course, a lot of you may not know this, but normally the owner of the company can be, or in most cases is, an employee of a company, right? You own the company, and then you set yourself as an employee of that company so that you can have a fixed salary, some sort of salary from the company. It's about separating you as a person versus you as a company. So if I do that, right, and I include myself and my inner circle as employees of the company, I could have a seemingly high average income. And I can say, well, look at that. I pay my employees on average this much. Now, we know, right, just from this basic example we've done, we know that that's actually not very representative, because a sample mean gives me the average value of an entire sample. But if I want to know the income of the average employee, notice how I move the words average around, then the sample median will give me that income. So sample mean gives me the average value of an entire sample. The sample median gives me the value of the average observation. In this case, the income of the average employee. People will not respect these definitions. So you'll hear someone say, the average millennial makes this much a year, and that could be a mean, that could be a median, that could even be a mode. And technically they're not lying, right? So you got to be careful whenever you hear the words average out there, because people will throw them, and there's two cases. Either people will not know the difference between mean, median, and mode, and then just use average to define whatever the best of their ability can understand, with no bad intentions, but still giving out an incorrect perception of your data. Or it could be people that do know what these mean and then purposely use the values that are most helpful or most useful for their point. I want to request federal funds. Let's say the COVID business or the COVID issue was very impactful for my business. I would like to request some federal or government assistance. I can say that the average employee in my company earns the sample median. I want to show my investors that my company is succeeding, my company is very successful. I can say that the average income in my company is this much. So again, you choose what you want to use based on what it is you're trying to show or prove. I know this makes me sound like a bad person, but I'm not like constantly lying with numbers. But I do want to give you an idea of how powerful these measures are and how other people can use them, because if you don't know this, then you're going to fall for this, right? So yeah, I'm not like inflating numbers or anything. Don't worry about that. Anyway, those are our 6 numerical measures. Okay? It's very important that you understand how to use these 6 numerical measures. And if you understand how to use them, right, then I would say you will be able to draw sound conclusions, or at least unbiased conclusions, right, from your data sets. I have an more or less, I would say, interesting example. And let me see if I can search it. So I really like playing around with my grades, because normally people say that a good teacher is going to have a bell curve, a normal distribution of grades, where the majority of their students show that they are average, because we understand that a majority of students are average. That's where the word average comes from. And then the extremes are going to be the really, really, really good students and the really, really, really bad students. So normally you would expect that the grade distribution of a good teacher looks something like this. Can anybody guess what my grade distribution looks like? Just guess. And if you've taken other classes with me, I think you'll have a better guess. Like that? Inverse bell curve, yeah. Actually, my grade distribution looks something like this. Which, does that mean I'm a bad teacher? I don't know. But essentially, it's actually a little bit less here, but essentially majority of my students are up here and then others are here, and very, very few students actually are in the middle. It's like I have this ability to identify students who are trying and students who aren't. And then, I don't know, maybe I unconsciously make my class better towards the majority of students who are trying, and then worse towards the students who aren't. I really don't know. But my grade distribution is really crazy. It's kind of like that. So my average is always somewhere around here, but my median is actually somewhere up here. So you'll see that I have a lot of averages of 70s and 72 and 75, but actually probably I never had any students that have had like a C value in a test or something, or in a specific test. It's just that because the low grades are very low, the high grades are very high, then that's why the average is somewhere in the C range. My median is actually a little bit higher. My median is actually B range. So if I want to show my supervisors that I am producing a very rigorous course, which I do, to be honest, my classes are very rigorous. But if I want to show that I am in line with the university's perception of what a good teacher is, I'm going to throw out an average of 70 something, because without looking at the grade distribution, just with an average, you hear an average of 70 something and you'll think that my grades fall somewhere in this normal bell curve. Well, this is C, B's, A's, D's, and F's. However, if you look at my actual distribution, it's not going to work that way. In the chat, it says a lot of the grade for this class is doing stuff at home, and students tend to do that or not, which gives them good grades or bad depending. That's absolutely right, and that's a really good example, right? In our homework, it's you either do the homework or you don't, which means that if you look at the homework grades, it's either 10s or 0s, right? There's no in between values, and that helps to push this even further away. Does it work? I think it does. At least I've seen a lot of success stories when it comes to my students. So I am going to keep working this way, because it does seem to work at least. Let me ask you something. And I took some grades. I'm obviously going to exaggerate these a little bit, just and simplify them just a little bit, just to kind of actually show what it is I'm trying to show. So let me pull up some of my grades here. So I took some grades from, it was one of the fluid exams I taught, and I just resampled them into 10 representative grades. And the average of those 10 representative grades was 90. You are a student in my class. There are 10 students. Again, I actually have 40, but I resampled this just to make it a little bit easier to calculate. So there are 10 students in class. We took a fluids test. In general, the sentiment amongst your peers is that the test was easy, and you found that the test was easy as well. Your grade was 90. The average grade was 90. My question is, if I were to ask you personally, how do you feel you stand in relationship to the rest of the students? Do you think you are among the best students in the class? Do you think you are among the worst? Do you think you are among the average? What do you think? What would your answer be? So the average is 90, there are 10 students, and your grade is 90 as well. You think you're pretty average with this grade? Okay. Middle? Okay, that sounds good. Any other ideas? Hypothetically, my self-esteem is not that healthy. Ah, all right, let's work on this. Good job. You're a good student. Does that help? I don't know. I don't know how to deal with students like that. All right, so if you want to know how well you stand amongst the rest of your classmates, do you think the average, which I haven't said what average it is, let me just spoil it now. Let's say it's a sample mean. Do you think this is a good measure for you to compare yourself to the other students? Because it seems like everyone's saying that if there are 10 students, the average grade was 90 and you got 90, that you are somehow in the middle. Okay, you are kind of like not that many better than you, or the same amount better, not that many worse than you. You're kind of like somewhere in between. But my question is, well, are you, right? Is there any other measure that you think may be more helpful to tell you how well you are doing compared to the rest of the class? Okay, let's try the median. So for this data set, actually the median was 100. It was a nice little take it or lose it test, right? You either had most right, you had not all of them right. It was a relatively easy test, just like your partner said. So how well are you doing compared to your classmates? Not amazing, good. In fact, the grade distribution, right? The grade distribution was actually, out of the 10 students, about 7 got a perfect score because it wasn't really an essay long test. It was just a couple of questions and you either had them right or you had them wrong. So about 7 students had a perfect score. One student got one of the multiple choice questions wrong. Another student got 2 multiple choice questions wrong, and another student didn't even try the test. So I just gave points for, for writing the name down. So out of 10 students, you actually aren't just in the bottom half, you're actually in the bottom 20% of students. Which is why these measures can be very tricky, right? They can be very tricky. And your professors, or maybe not your professors, but at least you should be very careful when you're using them to see how you stack up against the rest of your class. I used to like to do rankings. So I actually have a little sheet with everybody's grades, and I rank all my students. For some reason, I'm not allowed to just publicize rankings, which I think is kind of lame. I think some healthy competition is a good thing. It's like, oh, I'm number 5. I'd like to be number 4. But I guess I'm not allowed to do that. But I do like to keep rankings so that when I'm talking to a student and the student asks me, how am I doing in your class? Do you think I'm actually have a shot of passing or whatever? I can say, well, you're actually in the top 60% of my students. You're okay. Or you're actually in the bottom 30%. Well, I guess in the top 30, which is actually not very good. So in bottom 30. So what dictates the rankings? Just grades. I just grade everyone, and based on grades, I have little rankings. And I'm not sure if it was last semester or the semester before that, but before it became kind of like, before it wasn't official that I could or couldn't call people or tell people their rankings, I would call them by their numbers. So I had a student, I think I called him number 23 all the time. And at the very end of the semester, he asked me, hey, am I number 23 because of, and then he said some basketball player because he's a basketball player. And I guess some famous basketball player is number 23. I know nothing of sports. And I had to sadly say, no, you're the GOAT himself. Okay. I said, no, you're number 23. Oh, really? Then awesome. I said, no, you're number 23 because out of the 40 students in this class, you are the 23rd in terms of class, in terms of your grades. So yeah, it's nice to see how you're doing compared to the rest of the class. Now the good thing is that even for my class, even like up to number 30 had A's. So you can be number 30, still be an A student, and you can be number 31, still be a B student. So it wasn't that bad, not that bad. But the idea is, it's very tricky to use these numbers. And even people such as myself will try to use these numbers to show what it is I'm trying to show, right? I want to show professors that I am rigorous and my classes is difficult. I'm going to show my average. I want to show my students that I'm actually a very passable person in terms of classes. I'm going to show my median. And I'm not encouraging you to actively go out and try to lie to people, but you will at some point have a choice of choosing what measures or choosing what data to show to others in order to explain something. And you need to be very, very careful with that, right? You want to make sure that your message is conveyed. And let's assume for a second that we are all decent people here. So we want to make sure that the right message, the correct message is conveyed. And that is a message that includes all the relevant information that allows people to make the correct decisions. Assuming that we're all good people, which I highly doubt it, but I don't know all of you very well. Who knows? Okay. So those are the 6 numerical measures we're going to be using in this class. There's a little bit more that we can do with them. Okay. And I've already talked about median, so let me just follow up on that discussion. Let's say that you have a data set. All your data are here. If I want to split this data into, so I have all my numbers here, like all my measurements, or all my grades or something, all my data set, all my data values are here, all my data are here. If I were to split it down the very middle, okay, what would this middle point be in terms of the numerical measures we've talked about? Like visually speaking, I have my data set. Let's say it goes from a low value. I'm going to say this is my minimum value. Okay. This is my maximum value. And if I split it down the very middle, what value would this be? What measure would this be? The median, correct? If I want to find the length of this box, what value would that be? What measure would that be? The range, correct? And then, of course, the average can fall anywhere. Yeah, the average could be a little bit higher, a little bit lower than the median. It could be the median. Who knows? But let's not really worry about what the average is. Good. I could take this top half and split it also in half. And I could take this bottom half and split it also in half. If I do this, I am dividing, right, my data set into 4 quartiles. And I say that the first quartile, I'm just going to call it Q1, is essentially, right, the number that separates the bottom 25% of data points from the top 75%. The second quartile, which is also the median, is the value that separates the bottom 50% from the top 50%. And my third quartile is the value that separates the bottom 75% from the top 25%. So my quartiles, right, essentially are the values that divide, right, our data into 4 equal parts. So now in addition to the median, you have two more values, the first quartile and the third quartile. Second quartile is the median itself. But these values also help you identify, for example, let's say I want to give out an exemption from the final to the top 25% of students. In order to find the top 25% of my students, what I could do is I could take all of my students and divide them into 4 equal parts. And then the third quartile would split the top 25 from the bottom 75%. This will actually be very helpful, especially in terms of grades, right? Because if I say I want to exempt from the final anyone with an A, in my case, I would end up exempting more than half the class. That doesn't really work. So if instead I just divide my students based on number of students, right, then I could find a better way to split everything into, let's say, smaller groups, such as quartiles. I'm going to give you some data. I would like for you to see if you can help me calculate some of its measures. Let's see if we all understand this very well. This data is from, it's actually from a tape from the first figure in the first chapter of the book, but I think you can also find it in the first table of the 6th chapter of your book. Regardless, I am going to show you the data here so you can use it yourself. These are measurements for engine pull-off force, and we're going to be dealing with a total of 8 measurements here. So our 8 measurements are going to be 12.6, 12.9, 13.4, 12.3, 13.6, 13.5, 12.6, and 13.1. Let's say that you have these 8 observations, and I ask you to organize this data. When I say organize the data, what I'm asking you for you to do is to find all of the measures of this data, in this case, the numerical measures. Okay, so let's see if we can find those numerical measures. Let's start with a simple one. Let's start with the sample mean. How can we find the sample mean for these data? I mean, you don't have to give me the final value. You can just tell me what you would do. Okay, you would add them up and divide by 8. Yeah, that sounds good. So for my sample, I'm going to add up all of these numbers. I'm going to divide by the number of samples. In this case, you can see that the number of samples is 8. So I'm going to add up all these values and divide by 8. Sounds good. How much is that? Let's get our calculators, right? It seems that the final answer is going to be 13. Okay, good. So we found the sample mean. Now let's go towards the sample variance. So now, how can we find the sample variance? If I remember correctly, the sample variance was each element minus the sample mean squared divided by n minus 1. So it does look like we are going to have to make some additional calculations, right? We want to know what this minus the sample mean is, okay? So if I take, sample mean square is. So if I take 12.6 minus 13, that's negative 0.4, and negative 0.4 squared is 0.16. 12.9 minus 13 is negative 0.1, and negative 0.1 squared is 0.01. 13.4 minus 13.4 squared, 0.16. 12.3 minus 13, negative 0.7, 0.7 squared, 0.49. 13.6 minus 13, 0.36. 13.5 minus 13 squared, 0.25. 0.16, 0.01. So we have each individual measurement minus the sample mean squared and then divided by 13 minus 1, so divided by 12. That gives me a sample variance of how much? And you can take your time. We have enough time today. So we have 11.33. Okay. And remember that, I'm not sure if that number looks correct. I think it doesn't look very correct. Okay, that sounds a little bit better, right? 0.229. I think 0.229 sounds a little bit better for variance, because remember, variance is the square of the dispersion, right? So you kind of have a good idea based on the dispersion here. And so 0.229, I think that's correct. Christian, you may want to look at your calculations, make sure you don't have any calculating mistakes. Of course, I'm doing this by hand. I don't really expect you to do it by hand. I think you may find it easier to just solve this in a spreadsheet, but I'll leave that decision up to you. So now we find the sample standard deviation, which is simply the square root of the sample variance. In this case, Renee in the chat says it's 0.478. That does seem right? 0.4 seems like a good candidate for the square root of 0.2. So that's fine. Good. We found the first three numerical measures. I would like for you to let me know when we can move on, because I want you to calculate these, make sure you have the correct values, and make sure I have the correct values. So I don't want anyone to fall behind. So just let me know in the chat when you're ready to move forward. All right, good. It seems like a good number of students are ready to move on. When I say good number, I actually mean 4 out of 18. But using my statistical thinking, I would say 4 out of 18, but those are only the ones that are brave enough, right, to write. And I think it does represent most of the students. Oh, 5 out of 18, even better. Awesome, 5 out of 18. I think that's a statistically significant sample. If you do need some help catching up, that's also fine. We can definitely do that. But I'm going to start moving forward, and you can let me know if I'm moving too fast. Okay. The next value, the next numerical measure that we want to calculate whenever we're analyzing a data set is the range. The range consists of taking the maximum value and subtracting the minimum value. So in this case, we find our maximum value. It looks like it could be 13.5. Oh no, 13.6, right? And then we subtract the minimum value. So we have to find the smallest value in this data set, which it looks like it's going to be 12.6. So what is my range? 1.3. Oh, 12.3 is the minimum value. Oh, thank you. 12.3 is the minimum value. Thank you. So we have a range of 1.3, correct? 13.6 minus 12.3, 1.3. Good. The fifth numerical measure is the median. You find the median by arranging these numbers in ascending order and finding the middle value. If there is no middle value, you take the average of the two middle values. Okay, so we can work on it together. I can try here. Let's see, I have 12.3. And just to make things simpler for me, I'm gonna start crossing these out. I have 12.3, 12.6, 12.6. I have 12.9. I have 13.1, 13.4, 13.5, 13.6. So it looks like the median is going to be the number in between 12.9 and 13.1, which Renee already found it. That's obviously 13, correct? And the mode, it doesn't matter, right? If you do ascending or descending, the middle value will still be the same. And for context, the chat says I ordered mine in the other order. It doesn't matter. Yeah, it doesn't matter because it's the middle value. But you got to be careful because your quartiles have to be in ascending order, not descending order. The mode is the most recurrent value. So is there any value here that appears more than once or more than others? Well, yes. We can see that 12.6 appears more than others. Thank you, everyone. So our mode is going to be 12.6. So we have a sample mean of 13 and a median of 13. That's really nice. When they both align, it's really nice. We have variance, deviation, and then mode of 12.6. If I were to ask you, and hint, this is a trick question, but if I were to ask you which of these 6 values do you think represents the data better, or is a better representation of the data, what do you think the answer would be? Exactly. That's exactly the right answer, right? Renee says depends on what you want to represent, and that is the correct answer, right? You can't really pick one out of the bat. You need to know what it is you're trying to show, what it is you're trying to represent, and that's how you choose your values. Okay. After organizing our data, calculating all of its numerical measures, a useful next step is to tabulate our data. And let's just continue using this data for the example. If we can organize our data into tables, then we could try to use those as a way, okay, as a way to sort of visualize our data, although while still working with numbers. One of the tables that we're going to learn about is called the stem and leaf diagram. The stem and leaf diagram consists of dividing your observations into stems and leaves. Where essentially a stem is one or more of the leading digits and then the leaves are the remaining digits, or digit actually. So let me explain what I mean when I talk about stems, leaves, and these leading digits, right, and remaining digits. Let's pick a value here. We have 12.3. The stem and leaf diagram would require you to figure out what is the lowest order digit in your data set. It looks like all of our data points are up to 1 decimal point. So that 1 decimal point will be your lowest order digit. Everything else is a leading digit or digits. In this case, this is your stem. This is your leaf. So we're going to divide each of these data points into stems and leaves, and we're going to tabulate them. We can tabulate them by putting all of our stems in the same column. In this case, our stems are going to be 12 and 13, only 2 stems for this data set. And then all of our leaves in the next column. So for 12, I have 12.3, so this leaf will be 0.3. I have another leaf, 12.6, so I have 0.6. Another 12.6, so 0.6. 12.9, 13.1, 13.4, 13.5, 13.6. I want to make it clear that the leaf doesn't have to be a decimal digit, right? It could be maybe the last integer digit, right? It only depends on how accurate your data collection is. In this case, because we have collected data up to a decimal point, that's why our leaf is this decimal point. But if our data would have been only 12 and 13, our leaves would have then been 2 and 3, okay? So that is a nice little stem and leaf diagram. Now, for this data set, the stem and leaf diagram isn't actually very helpful because it doesn't really show us too much about the data. However, for larger data sets, for data sets with a larger range, the stem and leaf diagram is going to be much more helpful. And we're going to see an example before we wrap up today's class. In addition to finding or dividing your data into stems and leaves, sometimes it's useful to determine the frequency of your data. And the frequency is essentially a count of how many elements show up in a particular group. In this case, my first group is all of my numbers that begin with 12, and there are 1, 2, 3, 4 values that are in this group. My next group is 13, and there are 1, 2, 3, 4 values in this group. So stem, leaves, and frequency, where frequency becomes how often does a value occur, does an observation occur in a specific group. The stem and leaf diagram is not my favorite. I prefer more visual and less numerical methods of showing data, such as dot diagrams. It's important for you to understand stem and leaf diagrams because understanding these will help us into determining things like frequency distributions, which we'll talk about in a second. If we go to our book, and let me just grab my book as well so I can show the example. If we go to our book on chapter 8, we're going to have an example of a stem and leaf diagram with a much larger data set. And hopefully that will help us visualize it, at least in a way that showing the diagram actually becomes helpful here. Actually, not chapter 8, chapter 9 here. Oh, not chapter 9, chapter 6. Oh, I keep confusing my chapters here. We're module 9, but it's actually chapter 6. All right, so if you go to chapter 6, table 6.2, let me just move my camera a little bit so you can see it. This table shows a set of compressive strength, right, of 80 specimens. So we have 80 measurements, 80 observations. Each observation can be taken at its face value by calculating its numerical measures: median, mean, mode, range, sample variance, sample standard deviation. Now on figure 6.4 on the next page, we actually find a stem and leaf diagram for this table. Now you can see how the stem and leaf diagram becomes a little bit more helpful, a little bit more useful. In fact, looking at the stem and leaf diagram, again, don't focus too much on the numbers, focus on the overall shape. What type of distribution do you think this data follows? Exactly, Renee just said it in the chat. You can more or less see the normal distribution, right? You can see that the extremes are left with less values. We'll say for some exceptions. But then you can see that the majority of the values are in this range, the range of 150 to 160. Our frequency column tells us the same. We can see that lower frequencies are at the extremes, with a few exceptions, and the higher frequencies are near the middle of the data set. So here is where stem and leaf diagram becomes useful. Stem and leaf diagrams are more useful if you have larger data sets, because if you visualize, okay, they can help you visualize the dispersion or distribution of a set of observations while still giving you concrete numbers. You see a normal distribution, that really doesn't tell you anything about the individual measurements themselves, but a stem and leaf diagram does at least show you the individual measurements themselves. So what I would like to do now, throughout the remainder of the class, would be for us to begin using this data from table 6.2. If you don't have the book with you, you can also find this data in the notes. So you can look at the notes for today's class, and I have a screenshot of this table from the book. And my purpose here is so that we can try to use the data and see if we can find other ways to organize our data. All right. So if we want to organize our data, in addition to the stem and leaf diagram, another type of table that is very useful for organizing large data sets is a frequency distribution. Essentially, a frequency distribution consists of organizing your data into groups and then counting how many observations fall into each group or each sub-range. I'll give you an example of a frequency distribution, and then we'll just talk about how we can create one. You have your test grades, right? And you have all different grades. Let's say not just for my class, for any class. You can have a grade, and your grade can be any number between 0 and 100. Now, as nice as that is, it's not very helpful sometimes to try to deal with every single grade that every single student got. It just becomes a little bit, a little bit tedious. So instead, we can group our grades into several different bins. And each bin can consist of a range of grades. For example, I can create a bin, and I can put all of my students that had a grade between 90 and 100 in that bin. I'm going to call this bin A. I can have another bin for my students that had between 80 and, let's just use integers, so 80 and 89. That can be my bin number B. I can have another bin, and you can definitely see where I'm going with this. For students that have between 70 and 79, that can be C. Another bin for students that have between 60 and 69, that can be D. and a final bin for students that have between 0 and 59, that can be F. So your grades, your letter grades, are actually frequency distributions themselves. They are bins so that I can look at my grades and determine how many students had A in my class, how many students had a B, how many students had an F. There's actually a reason for F to be such a wide range of numbers. So sometimes I've asked myself, why can't we just, do a grade in terms of 20s, right? A 100 to 80, B 80 to 60, C to 40, D to 20, F to 0. But the reality is that most students are going to fall on the average, right? Most students are going to be average. That's the goal. So however you distribute your grades, a majority of students are always going to be kind of like in the middle. A minority will be on the extreme high, and a minority will be on the extreme low, but most students will be in the middle. If we make this middle, this C, 50, then what we're essentially saying is that we are going to have to pass students, right, who only understand about half the material. So the decision is made, right, to say that, well, in order for you to say that a student really understands the material enough to succeed and use it in the future, a student needs to know about 70% of the material, which is where that cutoff comes up at 70. Now, most students are going to be average, which means that most students that pass a class should fall in this average range, right, of 70. D's and F's, which are failing grades, then become, well, the remainder. You'll notice that other than the effect on your GPA, there is no significant difference between getting a D and getting an F, except for general classes where you can pass with a D. So a frequency distribution consists of taking my data set and lumping them into these little groups or bins, and then counting how many elements in each of these bins so that I can understand my data. There are several rules that we use to come up with frequency distributions. They're not set in stone, which means that we can move them around. But I think it would be a good place to start with these rules, right? One of the things we want is for the beans to be of equal range, at least by default. Now we already know that this isn't always the case. In the case of grades, the F bin is actually much larger than all the other bins. But again, we do this because it is the best way to analyze the data, because we know that a majority of students are going to fall in this bin. And for the most part, a majority of students do fall in this bin, except for my students. But because a majority of students are going to fall in this bin, we do need to make sure that our bins are representative of this normal distribution. Okay? So bins should have equal range, but we already know that there are cases where they don't necessarily have to have equal range. Sometimes it's impossible. Okay? We try to make sure that the number of bins is equal to the square root of the number of elements. So if I have 10 or 100 elements, I will try to divide my data into 10 bins. If I have 50 elements, I will try to divide my data into 7 bins, more or less. You can do 8, but I think 7 is a closer approximation. If I have 80 elements, I'm going to try to divide my data into 9 bins. So you're going to divide your data or your bins based on the number of observations that you have. So let's try it out. Let's see what that looks like. If we go back to our table 6.2, which is also in your notes, and we want to create a frequency distribution for that table. Then let's see, let's just try to follow this, these two more or less rules, not really rules, guidelines, let's call them guidelines. Let's see, the table 6.2 has 80 elements, 80 observations. If it has 80 observations, how many number of bins should I have? How many bins should I have? Okay, 8.9, but we can't really have 8.9. So I think 9 would be a good approximation. Thank you, Samuel, right? So root 80, but let's just approximate that to about 9. It's about the closest value. Now, what should be the range of each bin? So we know that the bins should try to have an equal range. So I guess our range of each bin should depend on the range of our table. So our table, just to give you, so that you're not looking through each value, our table has a smallest value of 76 and a largest value of 245. So what you can do is you can take that range, 76 to 245, and divide that into 9 equal spots. But that may not be very helpful. When you're dealing with larger data sets, it's just helpful to choose a range that covers your entire sample range. For example, instead of saying that we're going to draw a frequency distribution that goes from 76 to 245, which is the range in our table, I could say, how about 70 to 250? Because if I go from 70 to 250 and I have 9 bins, then that means that each bin should have a range of just 20. It just makes it easier. The math makes it easier. So remember, these are more like guidelines. They don't have to be exactly, they don't have to be followed to the dot. In this case, it's easier if I just, instead of going from 76 to the maximum, I can just go from 70 to 250, because that allows me to create bins with a spacing of 20, right? It's an easy calculation to make, okay? So I'm going to prepare my frequency distribution. And if you are curious about the calculations, then Renee has them in the chat, right? 250 minus 70 is 180. And then 180 over 9 is 20. Good. So let's go ahead and prepare our frequency distribution. My first bin is going to be from 70 to 90. And just to not have numbers repeated in the other bins, let's say it's actually from 70 to just 1 before 90. Okay, just like what we have here. We have from 80 to 89, right? So from 70 to just 1 before 90. If I look at my data set, and I'm not going to ask you to look at every single point, count every single point. I'll just count it for you. There are actually two observations that fall in that range. My second range is going to be from 90 all the way to 110. There are 3 observations that fall in that range. So all you're doing now is counting how many fall in this range. I can then go from 110 all the way to 130 and count that there are 6 observations. You can continue counting them, and the final results are in the notes, but try to solve it yourself as well. We did run out of time today, which is actually almost a first, but I think maybe next class we can perhaps go over the answers of this example and then begin with the next topic. So try it out yourselves, try to count the elements, make sure that your table matches the final answers, and I will see you on Wednesday.